In this lesson, we will delve into the principles and equipment of electrical discharge machining (EDM) technology, which is part of the special processing techniques in Project 2. As a crucial component of special processing, EDM technology overcomes the limitations of traditional cutting methods, achieving soft, overcoming hard, and bladeless cutting. We will explore its principles, equipment composition, processing characteristics, and practical applications, unveiling the mysteries of this unique machining technology. In traditional metal cutting processes, material is typically removed using the mechanical force of cutting tools. However, for materials with high hardness and toughness, or for parts with complex shapes, traditional machining methods often encounter numerous challenges. Electrical discharge machining (EDM) technology emerged as an important method within special processing techniques, offering new solutions to these problems. Electrical discharge machining (EDM) is based on the principle of material erosion through pulsed discharges to remove conductive materials. When the tool electrode and the workpiece electrode approach each other in an insulating working fluid, the voltage between the electrodes causes the fluid to ionize and break down at the closest relative point between the electrodes, forming a pulsed discharge. Within the discharge channel, a large amount of thermal energy is generated instantaneously, causing the local metal material to melt or even vaporize. These melted and vaporized metal particles are expelled by the explosive force and cool into small particles in the working fluid, thereby achieving material removal. From a physical perspective, the EDM process can be divided into 4 stages: ionization and breakdown of the dielectric between the electrodes, forming a discharge channel, thermal decomposition of the dielectric, melting and vaporization of the electrode material, and thermal expansion, expulsion of the electrode material, and deionization of the dielectric between the electrodes. EDM equipment primarily consists of a pulse power supply, a gap automatic control system, the machine tool body, and the working fluid, along with its circulation and filtration system. Pulse power supply. Its function is to provide the pulsed energy required for machining. The performance of the pulse power supply directly affects the efficiency and surface quality of EDM. Common pulse power supplies include RC pulse power supplies and transistor pulse power supplies. For example, transistor pulse power supplies have advantages such as a wide range of pulse parameter adjustments, high pulse frequency, and good processing stability, making them widely used in actual production. Gap automatic control system. Its task is to ensure that an appropriate discharge gap is maintained between the tool electrode and the workpiece electrode during the EDM process. If the gap is too large, the voltage between the electrodes cannot break down the working fluid, preventing discharge. If the gap is too small, it can easily cause a short circuit, affecting normal processing. The gap automatic control system automatically adjusts the feed rate of the tool electrode by detecting parameters such as the voltage and current between the electrodes to maintain a stable discharge gap. Machine tool body. It is used to mount and secure the tool electrode. and the workpiece electrode, and to facilitate their relative movement. The precision and stability of the machine tool body have a significant impact on machining accuracy. For instance, when machining high-precision molds, the machine's positioning accuracy and repeatability are required to be very high. Working fluid and its circulation filtration system. The primary functions of the working fluid are insulation, cooling, and chip removal. Common working fluids include kerosene and deionized water. The role of the working fluid circulation filtration system is to continuously circulate the working fluid, removing metal particles and heat generated during the machining process to ensure normal operation. Conquering the hard with the soft. EDM does not require direct contact between the tool and the workpiece. Instead, it uses electrical energy for machining. Therefore, the hardness of the tool electrode can be lower than that of the workpiece material. For example, for materials with very high hardness, such as hard alloys, relatively softer materials like copper or graphite can be used as tool electrodes for machining. Non-blade cutting, EDM, does not involve cutting edges in the traditional sense. It removes material through the erosive action of pulse discharges. This allows it to machine various complex shapes, such as micro holes, narrow slots, and intricate curved surfaces. For example, in the aerospace industry, cooling holes on some engine blades are difficult to achieve with traditional machining methods due to their small diameter and complex shapes, but EDM can easily accomplish this. High machining precision. EDM can achieve high machining precision, and the surface roughness can be controlled within a small range. By reasonably selecting machining parameters, precision at the micron or even submicron level can be achieved. No macroscopic cutting force during machining. Since there is no mechanical force involved in the machining process, deformation and residual stress are not generated, making it particularly suitable for machining thin-walled and elastic parts. Mold manufacturing. EDM is widely used in mold manufacturing. For example, the cavities of injection molds and die casting molds are often complex in shape and require high precision. EDM can accurately machine these cavities, ensuring the quality of the molds. Aerospace industry. Aerospace components often use high-strength, high-temperature, resistant materials and have complex shapes. EDM can be used to machine parts such as blades and turbine discs of aircraft engines, as well as some critical components of spacecraft. Electronics industry. In the electronics industry, EDM can be used to manufacture molds for integrated circuits and precision parts for electronic components. For instance, the molds for mobile phone casings and the machining of computer hard drive heads may utilize EDM technology. From the development of EDM technology, it can be seen that technological innovation stems from a profound insight into the nature of physics and a challenge to established paradigms. Traditional machining concepts held that material could only be removed through mechanical force, but EDM technology breaks this limitation by using electrical energy to achieve material removal. This inspires us to be bold in breaking away from fixed patterns and to courageously explore new methods and technologies in our studies and work. When faced with problems that cannot be solved by traditional methods, we should start from the fundamental principles and seek new solutions. Taking the machining of an aircraft engine blade as an example. The blade is made of high-temperature alloy material, which is characterized by high hardness and strength, and the blade's profile is complex with many small cooling holes. If traditional mechanical machining methods are used, there would be severe tool wear, low machining efficiency, and it would be difficult to ensure the precision and the surface quality of the cooling holes. By using EDM technology, copper electrodes can precisely machine the blade's profile and cooling holes. By reasonably selecting the parameters of the pulse power supply and the working fluid, the machined blade meets the design requirements and enhances the engine's performance. In EDM, there are several important parameters that need to be calculated and controlled. For example, the material removal volume is related to factors such as pulse energy and pulse frequency. The material removal volume V can be approximately calculated using the following formula. V equals KEFT, where K is a coefficient related to the material and machining conditions. E is the energy of a single pulse. E equals 1 divided by 2Cu. 2C is the pulse capacitance. U is the pulse voltage. F is the pulse frequency. T is the machining time. The derivation of this formula is based on the principle of energy conservation. The energy of a single pulse E is used to melt and vaporize the material. The pulse frequency F represents the number of pulses per unit time, and the machining time T determines the total number of pulses. The coefficient K accounts for the effects of the material's physical properties, the performance of the working fluid, and other factors on the removal efficiency. The selection of process parameters has a significant impact on the quality and efficiency of EDM. The main process parameters include pulse width, pulse interval, and peak current. Pulse width. As the pulse width increases, the energy of a single pulse increases, leading to a greater material removal volume, but also an increase in surface roughness. For rough machining, a larger pulse width can be selected to improve machining efficiency. For finish machining, a smaller pulse width should be chosen to ensure surface quality. Pulse interval. If the pulse interval is too short, the working fluid may not have enough time to deionize, which can easily lead to arc discharge and affect machining stability. If the pulse interval is too long, it will reduce machining efficiency. Generally, the pulse interval is reasonably selected based on the pulse width and the machining requirements. Peak current. As the peak current increases, the machining speed accelerates, but electrode wear also increases. In actual machining, it is necessary to comprehensively consider factors such as the workpiece material and machining requirements to select an appropriate peak current. With the continuous advancement of technology, EDM technology is also constantly evolving. In the future, EDM will develop towards high precision, high efficiency, and intelligence. For example, by adopting advanced pulse power technology and control algorithms, machining precision and surface quality can be further improved. Developing new types of working fluids and electrode materials can reduce electrode wear and enhance machining efficiency. Utilizing artificial intelligence technology can achieve automatic optimization and intelligent control of the EDM process. In this lesson, we primarily studied EDM technology. We first understood its principle, which is based on the erosion principle of pulse discharge to remove material. The process includes stages such as ionization and breakdown of the dielectric between electrodes, melting, vaporization, and ejection of material. EDM equipment consists of a pulse power supply, an automatic gap control system, the machine tool body, and a working fluid with its circulation and filtration system. Its characteristics include soft overcoming hard, bladeless cutting, high machining precision, and no microscopic cutting force. In terms of applications, it is widely used in fields such as mold manufacturing, aerospace, and electronics industry. We also demonstrated the advantages of EDM in actual production through case analysis. Additionally, we emphasized the importance of technological innovation, awareness, and the courage to break through traditional thinking. Finally, we introduced related calculations, process parameter selection, and the development trends of EDM. I hope that through this lesson, everyone has gained a deeper understanding of EDM technology.